Can I go? Thank you. Okay, so hi everyone. I'm Elia Pizzati. I'm a PhD student at Leiden Observatory, and today I want to talk a little bit more about what we can get with clustering measurements from JWST of quasars and galaxies. So Peter already gave a very beautiful introduction about clustering in general, so that makes my life easier. But I do wanna, if this allows me to go. Okay, I do want to go back to what Christina was mentioning this morning, which is the fact that the clustering does not give us information only about the environment, so the dark matter halo masses, but it's also telling us something about time scales in an aggregate sense, and talking about the duty cycles of quasars and galaxies. And we can try to understand these by taking for quasars, for example. So you see here like a drawing, like a sketch with some halos distributed, and in some of these halos are hosting bright quasars, which are like yellow stars. And the key point to understand is that like quasars are just subsampling the underlying supermassive black hole the population, just because supermassive black holes at some point, quite randomly, we think, may turn on and become active quasars. And so what we are really doing by measuring the clustering of quasars is really revealing this underlying supermassive black hole population, which is clustered in the same way as quasars. And so once we have these, so the green circles there, what we can do is just compare the number density of quasars to the number densities of these supermassive black holes to get the fraction of quasars that on average, the fraction of supermassive black holes that on average are active as quasars at any given moment. This is an average fraction, of course, and so it is telling us, on average, the fraction of time a single supermassive black hole is active as a quasar, and so this is the quasar duty cycle. So what we can do, like how we can measure this quasar duty cycle, so Christina already mentioned this morning that the Eiger survey measured for the first time the quasar-galaxy cross-correlation function redshift 6, so and also the galaxy-galaxy autocorrelation function, galaxy meaning all three line emitters. And we'll hear in the next talk by Jamu Huang from the Aspire, from the Aspire results. And so the idea is that we developed a simple model to interpret these kind of measurements, and the model we just take a dark matter volume simulation, and in a flexible way, really, we populate that with galaxies and quasars, so that we can respect the constraint from the clustering of quasars and galaxies, and also the constraints from their luminosity functions, because we want to have some faithfully realistic populations in the simulation. And so what we get in output from this model is a distribution for the halos that at any given moment are hosting bright quasars in red, and also the distribution for the halos that are hosting O3 emitting galaxies. And so if we assume that all these massive halos host the supermassive black holes, then the duty cycle is just this difference between the halos that are actually hosting bright quasars at this given moment and the total population of supermassive black holes. So it is this gap here between these two lines. And so you see that this gap is pretty big, redshift 6 at least, and indeed, as Christina was saying this morning, we measure a duty cycle that is less than 1%. And this has clear implications in terms of black hole growth, right? Because according to our standard picture, if we want to grow supermassive black holes, we need to make quasars shine at least for a few salpeter times, shine quite continuously, whereas what we're inferring with a very low duty cycle is something more very short and episodic accretions that somehow grows the black hole in a very short amount of time. That is not so dissimilar from what people have been arguing, like Kohei and Alessandro, more on Monday, for example, about super Eddington accretion, right? Christina made this point already this morning, but what also Peter said is that we can do the same for galaxies, right? The scale change, the axis change, but the concept is the same. And indeed, with Eiger, based on a 500 or so 3 emitters, we measure a duty cycle, galaxy duty cycle of around 15 to 20%. That implies that only 15 to 20% of the galaxies are emitting in O3 at any given moment. And that means, since we believe that O3 is somehow tracing star formation, well, this means that this is somehow a measurement of the burstiness of star formation redshift 6. And so we do have already a measurement of this burstiness of star formation, and it will be extremely interesting to push the boundary up to even higher redshifts and to see how this burstiness evolved with redshifts. The last point I want to make is about literate dots, because it will be extremely interesting also to look at the same properties in terms of literate dots. We have no idea. If they are AGN, can they actually grow their black holes? Will we measure a large duty cycle or a low duty cycle that may be hinting to super-Eddington accretion, as maybe Fabio was mentioning on Monday? But we do know one thing about literate dots, though. We do know that if we place literate dots in the same halo masses where we measure, that we measure for quasars, well, then we are overshooting the halo mass function. We are breaking lambda CDM in this case. So clearly, we know already that literate dots need to live in lower halo masses, and that is telling us that the literate dots and standard UV quasars, UV bright quasars that we're acquainted with, well, they may obey very different scaling relation because they may be living in very different halo masses. Okay, so that's I think I'm out of time, so thank you.
Thank you very much, Elia.